All right, so moving on, let's get into the actual tests. Um, so you don't have to memorize these formulas, but I do think it's important to understand a little bit about them. I mean, there's really no reason today to do stats by hand. Like, I can't, I think it's been about 7 years since I did a t-test by hand, but it is important to be at least somewhat aware of what the formulas are and how they capture these various things like sample size, standard deviation, and means, how those translate into the p-value that we've talked about. So, like I said, you'll do pretty much all your stats, as far as I'm aware, in R or in SPSS or even Excel. It's pretty easy. Um, but again, you do need to know some basics that go into this idea. And also, it is really important to just understand the concepts that go into these tests, kind of what they tell us, and also which test to use, which is of course, very important. So generally, when we're comparing means, there's two tests that we can do, or two tests that we typically do. There are others, but these are the big ones. One is known as a t-test. The other is known as an analysis of variance, or an ANOVA. So whenever you're comparing conditions, you're usually going to use one of these tests, t-tests or ANOVAs. So we'll start with t-tests. T-tests are used whenever you want to compare the means of two groups or two conditions or two treatments. All right. So the simplest designs, like comparing cell phones to no cell phones in a driving simulator, that would be a t-test. Okay. Now, t-tests as well as ANOVAs split into two types, so there's a lot of kind of branching going on here. But t-tests can split into independent samples and dependent samples. Independent samples are when groups are created through random assignment or class variables, right? So anything that's a between subjects design or a quasi-experimental design, you're going to use an independent samples t-test. And by the way, just as a refresher, remember quasi-experiments, this is when it's like an experiment, the hypothesis is the same, you're comparing means between two conditions, or actually could be more than two conditions, but you're not manipulating a variable, you're dividing people up based on an existing variable that they came into the study with, okay, like gender. So, and then you have dependent samples t-test. This is when the samples are not independent, but instead they're either matched or used as a within subjects design. Okay. So remember, matched is when you pair people up based on them performing similar at a baseline. Like if I wanted to compare two weightlifting programs and I matched people based on how strong they are before the experiment is done. Remember, within subjects designs is when you manipulate something and you have the same people do multiple conditions. Okay, that's a dependent sample. Um, I don't, I didn't do this. This is just kind of the way it is in the field. There's multiple terms that mean the same thing. So independent samples means between subjects, dependent means within subjects or matched. So just bear that in mind. Sometimes also be called repeated measures, meaning within subjects. And independent always means between subjects. Okay. So when you're looking at two differences between groups, there's a couple things you're going to consider. One is just how much they overlap, and also how much, um, well, actually, yeah, how much they overlap, but for two different reasons. One is how much do they overlap because of actual differences in the mean. Okay. So let's say these are sample means here. So we have our sample here, here, and here. And we calculate our standard error of the mean. Meaning, again, how much can we expect the mean to vary based on it being a randomly selected sample? Well, if we know that our mean could range, that our sample could range from about here to here, this looks like it'd be significant, right? Because there's not really any overlap. If we know that this mean, the true mean, population mean, is probably somewhere in this range, well, probability of, or this other mean, the true mean, the population mean is somewhere in this range, most likely. So that kind of suggests that the population means are different, right? If our two samples and kind of the amount we expect them to vary in terms of their means doesn't really overlap, well, then that would suggest that the populations we're drawing from are, in fact, two different populations, right? On the other hand, if we have two sample means and we get our standard error of the mean and that they overlap quite a bit, like you see with B, well, that's probably suggesting they didn't come from two different populations and there's not a significant effect. Okay. So that's what we're looking at here. Notice how they overlap quite a bit. So kind of what the true population mean might actually be for this one overlaps with what the true population mean might be for this one. So maybe there's no actual difference there. Of course, another factor. So that's kind of one factor you can think about. It's just how much overlap is there. There's actually a more formal way to do this with something known as confidence intervals. We're not going to cover that, but that is something people have been pushing for. So anyways, this one kind of here, this A-B scenario, actually meant to reflect, well, the drawing is not the best, but it's meant to reflect differences in the actual mean. So let's say we have a big difference between this mean and this mean. Well, that obviously suggests there is an effect, right? Let's say I'm looking at study strategy and you get a 20% difference between the two groups. Well, without even knowing anything else, like the standard deviation or standard error, that's probably suggesting there is a difference there, right? There is actually something going on. The other possibility is that the means are not bigger, are not more different, but the standard deviations and by extension standard error of the mean is different. So, for example, maybe we have the same actual absolute spread or difference between these two means, but the variance or the standard deviations differ. That can be another factor. And that also has a lot to do with sample size. We'll go into these concepts in more detail next, but I'm just kind of giving you an overview of things to think about. So don't worry too much about this example. So another way to think of this is let's say you find a difference of 10% on whatever dependent variable you're looking at, and you do that with only 5 people per condition. Well, that's not very reassuring, right? But let's say you get that same difference, but it's with 1,000 people. I think you'd feel more confident that there was actually a difference there, or there's actually a difference in the populations. And that's another thing that gets factored in. So we actually have 3 different things that mainly go into our formulas with t-test is how much do the means differ, how much do the standard deviation, or what are the standard deviations, and also what's the sample size. And each of these things are going to be factored in to our test, as we'll see. Another way to think about sample size would just be to go back to something random, like say flipping the coin. If you flip a coin and it comes out like, say you only flip it twice and you get 2 heads. Well, you wouldn't be very confident that it's a biased coin, right? Because I mean, getting 2 heads in a row is not that unlikely. What if you got, say, 2 out of 3 heads and 1 tails? Would you think it's biased? Probably not. How about out of 6? Say you get 5 heads and 1 tails out of 6. Would you think there's a unfair coin there? Probably not. I mean, it's like a small difference and it's a small sample size, right? Another thing is, let's say you flipped it 100 times and you got, I don't know, let's say like 60% heads or even 70% heads. Well, there your sample size is much bigger. So, or say you got 85% heads. Well, getting 85% heads, if it was like 5 out of 6, is not that unlikely, right? Because it's a small sample size. On the other hand, let's say you got that same score, but it's out of 100 or 1,000 or 10,000. Well, that would certainly suggest that there is actually something there, right? Because it's a bigger sample size and it's not going to be as variable. Okay. So in summary, these are 3 things that we consider and we use in our formulas when we're running t-tests, and really pretty much all tests involve these 3 components. Or I guess a little bit less with correlations, but don't worry about that too much. So first of all, what are these 3 things? What are the, just kind of common sense wise, what are 3 things that would make you confident there is a difference? One of it is, of course, the means being different. And the more different they are, the more confident you'd be that there's an effect, right? Another one being that the data are less spread out. So remember, going back to a while ago, when you draw from a population, and there's a lot of spread in that population, there's a high range of scores. Well, that translates into a higher range of means in your samples, right? Lastly, sampling more people is again going to be a big factor, like we talked about with flipping coins. So these 3 things all kind of combine into our formulas. And here's what that formula looks like. It doesn't, you don't have to remember this, but it's just, I just wanted to show it to you. So X bar is the mean for each condition. N is sample size, and S is standard deviation. So, well, actually, I'll just give you a second if you want to take this in, or you can pause the video to kind of think about what these might mean. So, in general, when it comes to t-tests, the higher the t value, the stronger evidence there is of an effect. Okay, that's how it works. So if you have a t value of 10, that's going to give you also a low p value, and it's going to say, yeah, there was very likely an effect there. If you have a t value of 5, it's less evidence that there's an effect. And if you have a t value of, say, 2, that's not very much evidence that there's a significant difference in populations. So on and so forth. If you get a t value of, say, 1 or even 0, that's no evidence of an effect. Okay. Or of a population difference, if you want to look at it that way. So with that in mind, just remember, keep that in mind as we're going through these. So higher t value, more evidence of an effect. Actually, let me just clarify though, that would be the absolute value. So a negative t value is still evidence of an effect. So -10, a t value of -10 or 10 both provide strong evidence of a population difference. It doesn't matter whether it's positive or negative. That just tells you what the direction of the difference was. So higher or low, further away from 0. You can think of it that way. The further away from 0 the t value is, the stronger evidence there is of effect. Okay, so let's kind of think about those 3 things we talked about. We talked about mean differences being bigger, we talked about data being less spread out, and we talked about sampling more people. So the first one is pretty evident, right? If a bigger difference in means is more suggestive of an effect, well, we could see that right here because we're taking the difference between two means. X1 is the mean of condition 1, X2 is the mean of condition 2. Okay. So with a big difference here, big difference between these condition means or sample means, it's going to give us a bigger t-value. Okay. Let me say that again. Bigger difference between these two means is going to give us a bigger t-value. Remember, a bigger t-value means more evidence effect. Okay. So that's part one. What about the spreading of the data? So remember, S is going to be your standard deviation. That's also factored in to the equation. So keep in mind that with a bigger standard deviation, again, it's harder to see an effect, right? It's harder to, or it results in more variance in your actual sample mean. Okay. So think about what this will mean here. If we're going to divide un minus 1 and then multiply that by a big standard deviation, well, that's going to shrink our t-value, right? So whatever this number turns out to be, and also whatever our sample size is, we'll get to the sample size next. The fact that you're dividing the top by the bottom, and on the bottom is your standard deviation, having a bigger bottom number is going to mean a lower t-value, right? Let me say that again. The bigger this is, or these are actually standard deviations, the smaller the t-value is going to be, right? Dividing by a big number is going to result in a smaller number than dividing by a smaller number, right? So that's how standard deviation is factored into your t-test. By the way, it's also very important to consider standard deviations when you're just thinking about whether there might be an effect or not. So let's say, again, I'm looking at some sort of memory test, and I'm comparing two study methods. Well, if the standard deviation of those scores, so the scores of individual people in both conditions, is like a lot, that kind of needs to be factored into the formula, right? Let me put that differently. So if you say just find a 10% difference in scores, or actually let's say you find a 5% difference in scores. Without the standard deviation, that doesn't really tell you much, right? Because I mean, it could be the case that people range from, I don't know, getting 0% right to getting 100% right and everything in between, right? So if that's the case, if people go all the way from 0 to 100 in both conditions, that doesn't really, finding a 5% difference doesn't mean much, right? On the other hand, let's say you find a 5% difference in test scores, but the standard deviation, so the amount that people typically vary from each other from the mean, is like 2%. Well, that's definitely suggesting an effect, right? Because the mean difference you saw is way bigger than the amount that people tend to vary from the mean. Okay, so that's why standard deviation is factored in, and also how it's factored. Okay, and then lastly, we of course have sample size. So remember we talked about how a bigger sample size makes you more certain of the effect. Right? So again, if we flip a coin, we get 100 times and we get 85% heads, chances are pretty high that the coin has been tampered with somehow. On the other hand, if we flip it only, let's say, 6 times, or something that results in 85%, but a small number, I mean, it's not that unlikely you could get 5 heads in a row or 5 out of 6 heads, right? So that's where we need to consider sample size again, because sample size adds precision, and it also, remember, cuts down on the variability of the sample mean. Okay, bigger sample sizes result in smaller sampling error. Okay, so that's again where we need sample size. Sample size is factored in here, and you could probably imagine how this would impact our results. So if we're dividing the mean difference by the pooled standard deviations, that's just this part here, but we're dividing that standard deviation by sample size. Well, having a bigger sample size would be would really result in a bigger t-score, right? And remember that t-score, a higher t-score is more indicative of an effect. A lower t-score is less indicative of an effect. Okay. So again, bigger sample size, typically a bigger t-value. We covered that, but again, those are the three things to consider. So t-value is going to be bigger when the mean differences are bigger, like we see here. The data are less spread out, like we see here. And we sample more people, like we see here. Okay. So those are the three main components of a t-test. Okay. And you could probably imagine what that would look like in terms of our sample mean and our kind of margin of error or our standard error of the mean. So, I mean, if we're drawing for more people and there's also less standard deviation, this bell curve is going to become skinnier, right? Same with this one. Thus, there's less overlap. If these two things are kind of shrunken horizontally, there's less overlap there. And if you widen them, there's more overlap, right? So that's where both the standard deviation and the sample sizes come into play. And again, if we have a bigger difference between this mean and this mean, that also means that the two are going to overlap less. Okay. Next up will be ANOVAs.